In this first module, we're going to look at three main topics. In the first two videos, we'll look at why plans so often turn out wrong. Next, we'll see the 6 levels of planning that occur in an Agile organization, and we'll see which ones Agile teams participate in. In the final video of this module, we'll define what makes a good Agile plan. The first problem traditional plans encounter is that tasks are assumed to be independent, but they aren't. To see why this is so, imagine we roll 5 normal 6-sided dice and add up the number of pips on those dice. In the case here, the sum would be 18. Suppose we do this a bunch of times, and we graph the number of times we roll each possible total. We'd get something like the results being graphed here. Sometimes when we roll 5 dice, we get all ones and have a total of 5. Other times, we'll roll 5 dice and get all 6s for a total of 30. Most of the time, of course, we'll be in between. And if we do it enough times, as I did to create this graph, we'll see totals of 17 and 18 most frequently. What we're seeing here is the good old normal distribution. We see some high values and some low values, but they balance out. We see lots of values in the middle. What I find interesting is that we're going to see this same shape even if some of our dice are loaded and always roll the same values. This is because of something called the central limit theorem. The central limit theorem says that the sum of a number of independent samples from any distribution will be approximately normally distributed. Suppose one of our dice always rolls a 6. The other 4 dice all roll normally, but this one die is loaded and always rolls 6. Now, the lowest roll we can get is 10. We'd get that if the 4 fair dice all come up with 1s, and the loaded die is, of course, 6. The highest roll we can get is still 30. Each of the 5 dice can still show a 6. Here are the results of simulating these dice 7,500 times. Now, what's key with the central limit theorem is the idea that the samples are independent. In our die rolling example, this means that the value on any one die doesn't influence the other dice. If you had one die that was magnetized somehow, then when it showed a 2, it flipped other nearby dice to 2. We would not have this nice normal distribution. Only when the samples are independent do we get this nice normal distribution shape to the graph. Now let's apply this to software projects. Instead of graphing the value on 5 dice, let's graph whether software tasks are finished early or late. We'd like to think we'd see the same shape to our graph, something like shown here. And the central limit theorem tells us we will have this if each of the tasks is independent. But let's see if that assumption holds. Here's part of a Gantt chart from a project I consulted to a few years back. Each of these boxes represents a task to import data from a particular file format into the system that this team was building. There were 5 different file formats to support, and each was, of course, different. The programmer on this thought about the 5 file formats and decided on a sequence in which he would do the work. The first format would take the longest because he would be building up some reusable code and a framework. He estimated 3 days to import data from format A. He estimated 2 days for each of the next 2 formats, and then a day each for the last 2. But when the programmer wrote the code to import from format A, it took 50% longer than planned. I asked him what impact he thought this would have on the rest of the schedule. He said, "Oh, no impact at all. I learned a lot doing format A, so the rest will go faster than planned. I'll still finish in 9 days total." Well, you can guess that this isn't what happened. I'm sure he did learn a lot doing format A. The problem here was that the nature of the work was highly correlated. If importing from format A took 50% longer than expected, our best guess of the other formats is that each of those will take 50% longer than initially expected. Let's tie this back to our mention a moment ago of the central limit theorem. Remember, the central limit theorem said we'll have some things way to the right and some things way to the left. But on average, they will average out and most things will be in the middle, if the items we have are independent. That's not the case here. If importing format A is harder than we initially thought, then format B is likely to be harder, and so on. It's like we are throwing dice, where if one die comes up a 6, it flips all others to a 6. What all this means for planning is that tasks are unfortunately not normally distributed. The times when a task takes longer to complete than expected are not balanced out by an equal number of times tasks take less time than expected. From experience, most of us would say that we finish tasks late, far more often than we finish early. In our next video, we'll continue to look at reasons why plans go wrong, starting with something called student syndrome.